tool. And I have, so it's called AI Base, I think. AI Space is the name of the tool. And let's honor the authors. Developed at University of British Columbia by these people here. Okay, so yeah, let's quiz ourselves. I've entered the network, all right, with these connections. And the network asks, is G conditionally independent of K given, and then these nodes with a thick blue circle, they have been observed. So this is a random generator, so here it has, you know, put lots of observations into the graph. What do you think? So, you know, what paths do we have? We have this path here, where we have a diverging connection. You know, it's kind of unreadable, but we still have the rules written down there, or at least you have them in your notes. So we have an observation, a diverging connection, which will block this path. We have an observation in a converging connection, which would mean that if we had that alone, it would mean that actually they would not be conditionally independent. However, we also have along that same path a connection in a serial, or an observation in a serial connection. So saying that this will block the path. And then we have a connection, so GBIK, where we have an observation in the diverging connection that will block. So I would argue that all paths are blocked and that these are conditionally independent. Does everybody agree? So I would like you to share the blame if it's wrong. Let's see. Get answer. They are conditionally independent. Okay. Let's do another one. So is A conditionally independent of K given these observations in the dark blue circles? So J would block this path, and incidentally we have no observation here, so that's yet another blocker along that path down the bottom. If we go via BIK, we have blocking serial and diverging connections. If we go that way, we have blocking serial connections here. So I would say that these are also conditionally independent. Let's see. Oof, okay. Lucky me. I don't want to play this too often because earlier or later I'm going to to get it wrong. Okay. But this is a good exercise. So, you know, why do we look at these networks at all? We can look at all of these probability tables, and this is now before making any observations. So we have a prior probability, A, B, C, D, these are the short names for the horses, and we have a prior probability for each of the horses that were in the first generation here to be carriers. That's a 1% probability, or pure, so meaning having both chromosomes healthy with a 99% chance. So this is the assumption based on a population of horses. And actually, all of those horses are known not to be sick, because if they were sick, they would have been removed from the stud farm. However, there's this new child, and later we will actually assume that this one has been sick, so this has 3 states, whereas the other variables just have 2 states. So the others can be, the other discrete variables can take the states carrier or pure, but this one can be carrier, pure, or sick. Okay, now we want to do 2 things. We want to calculate what are the probabilities, not having made any observations, of L being carrier 1%, pure 99%, or sick. It's not totally 0. I think it's 4 per mil or something, but you know, within the rounding accuracy here. And we could probably have figured that out. But then you can ask more interesting questions. You can now ask, you know, what happens if we make the observation that this one is sick? Then you know, we would probably infer that so if this one is sick, it can only be sick if both of its parents have been carriers. Because if one of the parents had been pure, the child would not have been sick. Okay, by these Mendelian genetics. So, you know, in our heads, we can figure out that if we make the observation sick here, then we will have 100% chance of being carriers here and here. But then how does this propagate? This is where things, you know, become harder to solve in your head. And this is where these graphical models are useful. So we'll now make an observation. I will observe that this is sick. And, you know, the first 2 positions here, that's, you know, as I argued just now, based on Mendelian inheritance laws. But the rest is more complicated. And you see that actually here the highest suspicion comes from this mother, which has engendered 3 out of the horses in the next generation. So this is the mother of F and G and I. And you see there has been some incest here. This was a brother and sister. And qualitatively, so qualitatively what you see, she's the mother of 3, he is the father of 2. Those are the ones that have the greatest probability of being a carrier. And well, the interest in this calculation is to, you know, from the owners of the stud farm to not use these carriers anymore in the breeding. So the probabilities for these horses that came in without any incest, so A, D, and E, they have marginally grown, so from 1% to 2%. But so we cannot totally rule out that these carrier genes, they could also come from A and E, but it's much more likely that they come from either B alone or, you know, B and C, for instance. Okay, so this sort of calculation we will be able to do at the end of the day. But before, we have to set up our graphical model. So we have to specify what these arrows mean or what these distributions look like. And here, for example, I have the following situation. So the probability table for J. J is a child of F and G. And now we have the following situations. They could be carrier or pure and so on. And then we have a certain probability for J being carrier or pure as a function of those. And to understand this probability table, I should get rid of this observation first. We can look at the table again. Yeah, now these numbers, they look perhaps more familiar. So where do these numbers come from? Let's do that in detail. So we're working on the example of the stud farm. And well, I should draw it because we will use that as a running example. so some of these horses are male and some are female, it does not, so it works out all right. So each child has a male father and a female mother, but I don't put down the sexes because they don't matter for us now. And we can now ask for the conditional probability that a child has any of the following states. It could be sick, or it could be a carrier, or it could be pure, given the state of the father and the mother. And the mother herself could be sick, or a carrier, or pure. I should have used capital letters here to say that these are random variables. And the father can also be sick, or carrier, or pure. And now we can practice Mendelian genetics. So if the mother is sick and the father is sick, then the child is definitely going to be sick with probability 1. So these numbers that I give are the probabilities for being sick, carrier, or pure. And these numbers, so conditioning on certain events, always have to sum up to 1. Now, if the father is sick and the mother is a carrier, then it could either have, so the child cannot be totally healthy. So it definitely gets a bad chromosome from the father, and from the mother it could get a good chromosome or it could get a bad chromosome, both with a chance of 1/2. And if the father is sick and the mother is pure, there's just one outcome. It's going to have one good and one bad chromosome, so it's going to be a carrier. And this table is symmetric. So we have these entries already. Now when both are carriers, that was really the case shown in the slide. When both are carriers, there are 4 possible outcomes, or 3 outcomes. One that the child is pure, one that the child is sick, and then there's a chance that the child is a carrier, gets one good and one bad chromosome. And the chances are 1/4, 1/4, and 1/2. Then if both are healthy, the child is definitely going to be healthy. And the last one we need is the father being a carrier, the mother being pure. And by symmetry, I can put that in here. Okay, is everybody happy with that? Now, this is a conditional probability table. And these are so important that in this field of graphical models they're sometimes abbreviated as CPT. So this table is good for John because, for L, because L could be sick or carrier or pure, but for all the others, we know for sure that they're not sick, or otherwise they would have already been removed from the stud farm. So if we know that both parents are not sick, then we can simply remove the first row and column of this table. And if we know in addition that the child is not sick, which was true for all of those here in the first two rows, then the state space can be further reduced. So we can reduce the state space from sick, carrier, or pure to only carrier or pure. But if we do so, we need to renormalize to make sure that if we sum over a random variable while conditioning on others, that we get out 1. So the probability that the child is either carrier or pure, given the father and the mother, and reduced as follows. So the mother can be carrier or pure, and the father can be carrier or pure. So now we have already eliminated the first row and column, and now we can eliminate the entry that corresponds to sickness. And so here altogether we have then 2/3 versus 1/3. Then we have 1/2, 1/2. Symmetry is the same down here, and here we remain with 0, 1. So to set up the graphical model, our Bayesian network, we assume the family relations as shown in the picture on the left. Then we also assume that all horses except John are not, except the last one. All horses except L are known to be not sick, so we can reduce these probability tables. And we assume a prior probability for instance of horse number A being a carrier or pure is 1% and 99%. Okay, and using this information, we can now set up the graph. That was shown here. And so if we look at this probability table, for instance, this is just the one that I wrote down now. This would be 2/3, 1/3, 1/2, 1/2, and 0, 1. Those are the 4 entries of the probability table that we just created. Okay, so the graphical model is fully specified now, and I've done so really, by clicking together all these nodes and creating edges and creating these probability tables, and we can now start and do inference. So, for instance, compute the probability that L is a carrier, pure or sick, and later on, vice versa, see what happens if we inject some observations. So, for instance, we may ask the question, what is the probability of L being sick or a carrier or pure, irrespective of what the others are. And if we forget everything about graphical models, we can write that, so I'm abbreviating this just as P of L. We can write this as summing out A, B, C, D, E, F, G, and so on. So summing out up to K out of the joint probability. And again, forgetting about graphical, so this is just the marginal. This is what we want to compute. And I can obtain this marginal if I want by rewriting this in terms of conditional probabilities. So I could have, for example, the probability of L given A, B, C, D. I'm doing this explicitly. And K times the probability of A up to K. And now I can use this iteratively. This is, of course, not how we're going to do it, okay? But I just want to stress what would be the naive or the costly way of doing that. So we would have PL given A up to K times K given A up to J times the probability of J given A up to I. You see where I'm getting it. Given A up to H. Okay, and perhaps this is getting too boring. So the last terms would be probability of B given A times P of A. So that is possible. But we can do, if we assume, we can do much better if we assume these conditional independence relations. And this is why this notion of deseparation and so on is important, because now I can simply write that this is the summation of A up to K of, so for example, L depends only on J and K and not on all the others. Then K depends only on H and I and not on all the others. J depends only on F and G and so on. Well, I will actually finish this explicitly. So J, and then we have just to make the point that even if I write it all down, this is still going to be much cheaper. Okay, and we can now look at the number of entries that we need to store in a probability table to use either the one or the other computation. So the joint, and by the way, I'm missing the L here. So what is the size of this joint distribution? I have two possible states for A, it can be carrier or pure, two possible states for B, which can be carrier or pure, two possible states for C, and so on. And I have three possible states for L, which can be sick, carrier, or pure. And altogether I have so altogether these are 11 cases, and I need to multiply all of them to get the number of entries in the probability table. So this is 2 to the power of 11, because it's 11 variables with 2 states each, times 3. I didn't do this in my head. This is more than 6,000 states, or configurations, or entries in this joint probability table. And if I use more than just 2 states per variable, so let's say you work in image processing and you want 256 states for each variable, you know, this gives you totally astronomical numbers. Now, if we look at this, this table here has just 2 states. This table here has 4 states. This table here would have, again, the 6,144 states. So if I sum up all the states that I need for this naive formula, which disregards the conditional independencies, I have more than 10,000 entries. And now contrast that with the last expression here. So here L has 3 and J and K both have 2. So 12 states for this first variable. And then we have 8 for this one. 8 for all of those, in fact. Okay, these states, now if you want to compute the amount of storage we need, you don't need to multiply these states, you can just add them up. And I find that I overall need only 70 entries. So this is one part of the gain that you incur when you take these conditional independence relations into account, and this is why they're so important. But we can further simplify. Do you have an idea when you look at this expression, and if you wanted to compute this explicitly, what you would do about it?
Well, you can sum over only one variable and then compact it, so you only have 8 for that, and then you sum over the next variable and compact it again. And,
yeah.
Go like this, so every time you only have 8.
Yeah, very good. You have just invented the probably most important algorithm in this whole field, which is variable elimination. So the observation is that, so if we look, for instance, what depends on A, then this term depends on A, and that term depends on A. So we could rewrite this expression by taking, the summation over A at the very end, and well, shifting those 2 terms that depend on A along with it. And then so if we do that, we get, I'm leaving the rest as it is. So we have the summation of B up to K. And then we have all these terms. And then at the end, we sum over A. And of the terms that depend on A. And if I want to express that in some abstract fashion, I would say this becomes a new function. Or in this field, people say this becomes a factor of, I've summed out A, I have eliminated A. So this is a function that depends, or a probability table that depends on F and B. Now we can move, for instance, the summation over B. So this will, of course, have to stay within the summation over B. Then we can collect the other terms that still depend on B, and so on. So we can integrate the variables out one by one, but the the results of these integrating outs will typically depend on some other variables, except if we had a totally trivial graph. And this leads to fantastic savings, and this is what is at the core of variable elimination. And after the break, we will do that explicitly. And then also, you know, there are many ways. So I could start by summing out over A, but I could start summing out over some other variable. And which is the proper way? We will discuss that after the break.